Welcome back to the Deep Dive. We streamline complex research so you can get instantly well-informed. Today, we're tackling something that honestly feels like a core weakness in a lot of current AI agents. These long-running LLM agents, they're just forgetful.
That really is the nub of the problem, yeah. I
Mhm.
mean, these models have incredible power, huge context windows even, but it's like Groundhog Day for them. Every new task, they treat it like they've learned absolutely nothing from the past. All that valuable history, interactions, mistakes, mostly just gets thrown away.
Right, so they repeat errors, don't build on insights, they fundamentally lack self-evolution capabilities, it seems.
Exactly. They can't learn those life lessons, so to speak.
So the potential breakthrough we're discussing today is about changing that, turning that messy, unstructured history into something useful, like actual rules or strategies.
Precisely. We're looking at a framework called ReasoningBank,
Mm.
and alongside it, a scaling strategy called MAT-EDES, which stands for Memory-Aware Test Time Scaling.
Okay, Reasoning Bank and MAT-US.
And the mission here, really, is to unpack how these systems could fundamentally alter how agents learn. ReasoningBank aims to shift the agent from just being a passive logger, just recording what happened, to an active learner that distills actionable strategies from that experience.
So the agent gets smarter over time, its efficiency actually compounds.
That's the promise. It
Mhm.
becomes more capable, more efficient the more it does.
Okay, let's start with why this is even a problem.
Mm,
We see LLMs handling massive chat histories now. Thousands, tens of thousands of tokens. Why can't they just use that memory across tasks?
Yeah, it's a good question. It's not really about the amount of storage. It's about um, the usability and the quality of what's stored. Transferability, really.
Yeah.
Current approaches, the baselines, they tend to fall short. On one side, you have systems trying to store, like, the raw interaction logs. Think of something like Synapse,
Just everything that happened.
pretty much, which is, maybe useful for debugging by a human. But for the agent itself, it's way too long, too noisy, it can't easily pull out the useful bits for a totally new situation.
Right, gets bogged down in the details. So what about simplifying that log? Are there methods that try that?
Yeah, that's the other main approach. Things like AWM agent workflow memory. These focus only on storing routines that worked, successful workflows.
Okay, so they learn the happy path, like the exact clicks to buy something on one specific site.
Exactly. They capture common, successful procedures.
Mm.
But that's still quite limited. It doesn't really capture the higher level reasoning. You learn the path, maybe, but not the general strategy for finding paths on any site.
And if these systems are only storing successes, where's the gap? What are they missing?
Well, arguably, they're missing the most valuable learning opportunity:
Mm.
failure.
Ah, interesting.
The sources we looked at really hammer this point home. Existing memory designs focus way too much on success. They basically ignore or discard the lessons buried in the agent's own mistakes.
So the memory just becomes a passive record, not an engine for getting smarter or more general.
Precisely. It's not actively helping the agent generalize or avoid past pitfalls.
Okay, that's a critical insight. If learning needs both success and failure, we obviously need a smarter way to structure that memory. How does Reasoning Bank actually distill these lessons?
It works by creating these structured knowledge units. Think of them less like raw data logs and more like concise, transferable strategies,
Yeah.
high-level takeaways. And this structure is really designed to make the memory abstract enough to be useful across different kinds of tasks, different domains.
So it's not just a pile of text, it's more like a set of formalized lesson cards.
That's a great analogy, yeah. Each memory item in Reasoning Bank has basically three parts. There's a short title, like a headline for the strategy, then a one-sentence description summing it up, and finally, the content, which details the actual reasoning steps or the operational insight.
And that abstraction is the key difference.
Absolutely. A memory item wouldn't be click button ID by now 345.
Yeah.
It might be something like strategy. Check for hidden filters and drop-down menus when search results seem too broad. That's useful anywhere.
Okay, that modularity makes sense for transferability.
Yeah.
So walk us through the cycle. How does an agent actually use this reasoning bank and then contribute back to it, the closed loop?
Right. It starts with retrieval. So before the agent even acts on a new task, it queries its reasoning bank. It uses, like an embedding search, to find the top K most relevant strategies from its past.
And those strategies get fed to the agent.
Yeah, they're injected right into its system instructions, its prompt. So it starts the task with relevant advice, essentially.
Okay, so it's primed with potential strategies. It then attempts the task. What happens next? How does the system figure out if the attempt was good, bad, or worth remembering?
That's step 2, construction. After the task attempt, the agent uses another LLM, basically acting as a judge to label the outcome, success or failure.
And this is self-judgment, no human needed.
Critically, yes, it's self-judgment. It doesn't need external ground truth labels. The agent assesses if it met the task's objective based on, constraints or observed results.
And then the loop closes with consolidation, putting the learning back into the bank.
Correct. If the attempt was judged a success, that validates the strategy used, reinforces it. But, and this is the really interesting part, if it was judged a failure.
It learns what not to do.
Exactly. It provides these crucial preventative lessons, counterfactuals, like don't try X in situation Y because it leads to Z error. Both the good and the bad insights get distilled, structured, and added back into the reasoning bank.
So the whole system gets incrementally smarter with every single task attempt, success or failure. Continuous evolution.
That's the idea. Strategic evolution built from experience.
Okay, so ReasoningBank gives us the structure, the mechanism for learning. But you also mentioned MATI-S, memory-aware test time scaling. Where does that fit in? I guess you need good data to create good memories.
You nailed it. Reasoning Bank is the engine for distilling knowledge, and MATI-S is about generating better fuel for that engine, richer, more diverse experiences to learn from. Traditionally, when we talk about scaling AI, we often mean scaling breadth. Run the agent on thousands of different simple tasks.
More data points.
Right. But MATS flips that. It focuses on scaling experience through depth. You allocate more computational effort to explore a single complex task more thoroughly, generate multiple ways to tackle it.
So instead of just one quick attempt, you're really exploring the different corners of the solution space for the harder problems.
Exactly. You get more diverse attempts, maybe find novel solutions, or really understand the failure modes for that tricky task.
And how does this connect back to the memory?
Well, the source material highlights this really nice synergy. The existing high-quality memory in Reasoning Bank helps guide that deeper exploration. It steers the agent towards more promising path, so you're not just exploring randomly.
Okay, so the memory makes the exploration more efficient.
Right. And then, in turn, the rich data generated from that deep exploration. That forges even stronger, more nuanced memories to put back into the bank. It becomes a positive feedback loop. Better memory leads to better exploration, which leads to even better memory.
That makes sense. So how does MATI-S actually do this deep exploration? What are the implementations?
There are two main ways described. The first is parallel scaling.
Okay, parallel suggests multiple things at once.
Yep. The agent essentially generates multiple different trajectories or rollouts for the same query simultaneously, like trying several approaches in parallel.
And how does it make sure the memory it creates from that is actually good, not just random noise from one weird attempt?
Good question. It uses a technique called self-contrast.
Self-contrast sounds like it's comparing its own attempts.
That's basically it. It looks across these parallel attempts, compares the different trajectories. It tries to identify patterns that are consistent across the successful ones and filter out solutions that only worked once, maybe by chance.
So it's looking for reliable, repeatable strategies, not just flukes.
Exactly. It helps ensure the distilled memory items are robust and genuinely transferable.
Okay, that's parallel. What's the other approach? You mentioned sequential.
Right, that's sequential scaling. This relies on the idea of self-refinement.
Self-refinement, improving as it goes.
Yeah. Instead of multiple parallel runs, here the agent refines its reasoning within a single trajectory. Maybe it hits an error or gets feedback, and then it corrects its course during the task.
Like backtracking or trying a different substep?
Precisely. In those intermediate steps, the notes it makes, the corrections, the agent realizing, oops, that didn't work, let me try this instead. That whole refinement process generates really valuable signals for memory. It's high-fidelity data about how to overcome obstacles.
Got it. So we have the memory structure, Reasoning Bank, and the deep exploration method, MATI-S. Let's get to the results. Does this combination actually deliver? What do the benchmarks show? Things like WebArena, SWE Bench, those are tough.
They are tough, and the results reported were, well, quite striking, not just small bumps. Reasoning Bank consistently beat the baselines the agent with no memory at all, the one using Synapse, raw logs, and the one using AWM, success workflows.
How much better?
Across the board, they saw improvements. In some cases, up to a 34.2% relative improvement in the overall task success rate compared to the memory-free baseline.
Wow, over 34% relative gain? That's significant. That suggests it's really learning something fundamental.
It does. And what was particularly interesting was where it showed the biggest gains.
Generalization, transferring knowledge.
Exactly. It performed especially well on the really challenging generalization tests, things like the Web Arena multi-subset, which involves complex instructions, and the Mind-to-Web cross-domain tasks, where it has to apply skills learned on one type of website to a completely different one.
That's the real test, isn't it? Proving the memory isn't just site-specific tricks, but actual abstract knowledge.
Right. It suggests the curated memory is more robust, more transferable to situations the agent hasn't seen before.
Okay, so it's more effective, but is it more efficient? Because, one frustration with current agents is watching them go down these long, useless paths, racking up interaction steps and API calls.
That's a crucial point for practical use, absolutely. And yes, the results showed superior efficiency too, up to a 16.0% reduction in interaction steps compared to the other memory methods.
16% fewer steps. Now, is that just because it gives up faster when it's failing? Or is it actually finding the solution more quickly?
That's what they looked into, and it's the latter. The analysis was pretty clear. The reduction in steps was most noticeable on the tasks the agent actually succeeded on.
Ah,
For example, on successful Web Arena tasks, the agent with ReasoningBank took, on average, something like 2.1 fewer steps to get to the right answer compared to the baseline, with no memory.
so it's genuinely finding the efficient path more often, not just failing faster. The memory is acting like a guide.
Precisely. It's steering the agent towards effective reasoning right from the start, saving time, steps, and presumably compute cost.
Okay, and let's circle back to that idea you raised earlier, the importance of failure. How crucial was learning from mistakes in these results?
It turned out to be critical. And this is where ReasoningBank really stood out from the pack. It was apparently the only memory system they tested that consistently got better when it included failure trajectories in its learning.
Really? The others got worse.
Some did, yeah. Baselines like AWM, which focus only on success, actually saw their performance degrade when they were forced to learn from failures. It seemed like the failure data just added noise or confused them.
Like they were being poisoned by the negative examples.
Kind of. But ReasoningBank, because of its structured approach, was able to turn those failures into useful, constructive signals. There was one test case mentioned where adding failures boosted its success rate from about 46.5% to nearly 50%, 49.7%.
So it's the difference between just ignoring mistakes and actually analyzing them to build a what not to do checklist.
That's a perfect way to put it.
Yeah.
And this structured learning from both success and failure leads to some interesting emergent behaviors over time.
Like the strategies themselves evolve.
Yeah. The paper noted that the knowledge stored in ReasoningBank seemed to progress. Early on, it might capture simple procedural stuff like find navigation links. But over the agent's lifetime, you start seeing more complex compositional strategies emerge.
Can you give an example?
Something like a memory item evolving to include steps like cross-reference the current task requirements against limitations observed in previous domains, then reassess the initial options before proceeding. That's much higher-level strategic thinking being built.
That really does sound like genuine learning and evolution.
It points towards that, yeah.
Okay, so as we wrap up this deep dive, the big takeaway seems pretty clear. If we want agents that truly learn and improve, the design of their memory has to fundamentally shift.
Absolutely. It needs to move beyond just passively storing what happened, those raw trajectories, and towards actively distilling why things happened, capturing those transferable reasoning strategies.
And crucially, embracing the lessons from failures, not just successes, seems key to enabling that real self-evolution.
The future power of these agents might really hint on how well they can structure, refine, and compound knowledge, not just how much data they can access or store.
This whole evolutionary process, this learning loop, it seems to rely quite heavily on that one component you mentioned earlier, the LLM as a judge, the part that decides success or failure.
That's true. The self-judgment mechanism is central.
So this brings us to a final thought, something for you, the listener, to really chew on. If the entire knowledge base, the agent's evolving intelligence, is built on its own judgment, what happens if that judge LLM is flawed, or has biases, or just makes systematic mistakes in certain situations? Could an agent accidentally learn the wrong lessons? Could it cement bad strategies, misremember failures as successes, because its own internal judge got it wrong?
That's a really critical question. If the system has no external reality check, how do you prevent this self-generated knowledge from becoming polluted over time? What safeguards are needed to keep that learning loop grounded and, well, honest?
A profound challenge, especially as we think about deploying more autonomous agents. Definitely something to keep in mind. Thank you for joining us on the deep dive. We'll see you next time.